Hello, everyone. Today, I'd like to talk about how we use the Feature Store and the Vertex pipelines in our fraud prevention system. First, let me introduce myself. I am an engineer of machine learning in the fraud prevention team. I joined Merpay as a new grad in 2019. I have been working on machine learning solutions for fraud prevention, such as chargeback detection. Recently, I have been involved in the development of Vertex AI-based machine learning pipelines. Okay, today we will go through 4 parts. First, we will briefly introduce the background of the system and why we need to use Feature Store and the Vertex pipelines. Second, we will talk about the Feature Store utilized in the system. Third, we will introduce its training developing pipeline. And finally, we will make a summary and talk about the future works. Let's talk about background. In order to handle the growing requirements, so far we have multiple fraud detection related solutions in our system. Alert filtering is a system that aims to improve the quality of fraud detection systems. By reducing the false positive rate, it reduces the number of rule-based fraud detections and finally reduces the operational load. Chargeback is a bank-initiated refund for credit card purchase, and chargeback detection is for detecting it as soon as the transaction happens. And also we have suspicious account detection and suspicious action detection. Please check our previous tech blogs for more details if you are interested. Before introducing the latest architecture, I'd like to introduce our legacy fraud prevention system first. For each task or solution, we created an independent pipeline on a unique platform and also choose its own framework, which could all be different from each other. They fetch the data from all different kinds of data sources, such as GCS, BigQuery, and spreadsheet reports. For each machine learning solution, it has its own pipeline to train and deploy the machine learning models. It also has a unique way of serving. For example, alert filtering has its serving pipeline on GKE and fetches the online features from Spanner. Chargeback detection has a prediction pipeline based on Airflow and fetches the data from BigQuery. And other non-machine learning solutions, like sub-account detection, also have their own independent ways of fetching input data and providing services. Although all the solutions work independently, they all have the need to create features from data sources. Some solutions, like machine learning solutions, also share the common methodology to train and deploy models in a similar way. So let's talk about features first. As the number of solutions grew and the model became more complex than the initial version, the total dimension of the features increased by 4 times within 1 year. These features become various data sources, like BigQuery, Spanner, GCS, and even spreadsheet. Features used in training and predicting could have different data sources. Some of the models need to predict in real time, so they need to use Spanner in predicting for lower latency. But the training, they usually use BigQuery or GCS since Spanner usually costs more. Models like chargeback and alert filtering Although the targets are different, their features still have shared some similarity. Since the feature creation in different solutions are independent, some of the features may have been created multiple times for different models. Here is a graph as an example which we can use to explain the relations between features. Feature X is used in both Model A and Model B at training. In legacy system, it's been created multiple times separately when we execute different pipelines at the same time. And for feature X and Z used in Model B, at training, they are created from BigQuery. When predicting in the production, the data source is changed to Spanner because Spanner helps the query real-time helps us to query real-time data in lower latency. There are two main costs around features. The first one is the cost of maintenance. A large amount of the features is difficult to maintain, and we need to spend lots of engineering resources on it. The second one is computing resources spent on creating features from data source. For these two costs, we are proposing a way to cut them both down. We can reduce the cost by reusing features between different models. In conventional ways, the similar or same features would be created and maintained separately. By then, lots of resources would have been wasted. But if we merge them together like this picture, we can reduce both computing and maintenance costs. After finding out the way to better organize and manage features, I'd like to talk about another problem in legacy architecture. In the legacy architecture, each model has its own training deploying pipeline and works separately. In alert filtering, this left graph, it gathers data from other microservices and creates a table in BigQuery for training the model. The model training is done through AI platform training jobs, and the model is deployed to AI platform models. During the prediction, the features are created and saved in Spanner, passed to the deployed model by pipelines run on GKE, and send the prediction results to another system as the output. In the right picture, the chargeback detection. The dataset is created from spreadsheets and BigQuery from other microservices, and it's saved to BigQuery for training. The training and the deploying is in the same way with the alert filtering, which are done by AI platform jobs and models. The prediction part is different from alert filtering. It's controlled by Airflow. As we can see in the graph, a general flow of pipeline consists of the following parts. Creating training set from data sources, training models through AI platform jobs, and deploying on AI platform models. In the production, predicting inputs are created from data source and sent to the deployed model for the prediction result. And then the result will go somewhere needed. In the legacy architecture, all the machine learning solutions can be concluded as this graph, but they are all independent. So we can share the fundamental part between pipelines, the part of getting training set, training model, and deploying models for serving. They are all the same for all the machine learning solutions. As a conclusion, machine learning solutions have a common training deploying process. The training sets are saved in BigQuery. The model are trained by AI platform training jobs, and the models are deployed on AI platform models. The main difference between each solution is the predicting process. They usually have different inputs and outputs. For example, the input from BigQuery, Spanner, or even spreadsheet. The predicting output is usually to connect to different microservices or systems. By summarizing what we discussed so far, two main problems about features and architecture are coming out. For features, we spend unnecessary resources on creating and maintaining duplicated features. At the same time, we want to improve data reliability, which means we want to have make sure the data used in prediction are created in the same way as training. For architecture, we want to have a shared training deploying pipeline, which will make it easier for ML engineers to improve the current models or deploy new models efficiently. Here, I'd like to introduce our new system architecture. We will mainly be talking about two parts: a feature store for all models and a common pipeline for training deploying process. Here we have our new architecture in the graph. In this new architecture, predicting pipelines, monitoring, and outputs are different for each solution, but the part of the feature store and the training deploying pipeline are shared. We will introduce these two parts next. And let's talk about the feature store first. Here is our conventional way of creating features. Each solution has their own process of creating features from data sources. Some models even have two ways to create features in training and predicting, like this model B, which turned out to be a lot of similar features pipelines that need to be maintained. By introducing the feature store, the data sources no longer need to be handled by the model pipelines themselves separately. All the features will be created together and managed by the feature store. Models no longer in training or predicting can fetch the features they need from the feature store directly instead of accessing the data sources and creating by themselves. Let's explain the feature store a little bit more. A feature store is an ML-specific data system that runs a data pipeline that transforms raw data from data source into features, and it stores and manages the features by itself. Then it serves features consistently for training and inference purpose. As this graph shows, after data scientists define the features, it will transform the ingested data into vectors for model training, serving, and even for data analysis. We used to have two candidates for the feature store. One is Vertex feature store, another is Feast. We'll compare them in three ways. The first one is whether it supports stream ingesting. As already mentioned previously, some of our solutions need real-time prediction. The prediction input needs to be created in real time, which means the feature store needs to support stream ingesting. The Vertex feature store only supports batch ingesting in the official documents. Meanwhile, Feast can ingest while streaming. with streaming. The second one is GCP support. Our development is basically on GCP, and we wanted the feature store to support GCP as much as possible. From this perspective, the Vertex Feature Store is a GCP native application, since the Vertex AI is the latest AI platform product provided by Google. The Feast is not a native of GCP, but it supports GCP well after version 0.10. The last one is the cost, the price of using it. At our calculation, Vertex Feature Store is more expensive than the Feast. So we choose to use Feast as our feature store for now. So for us, how to use Feast? Before starting, we need to do some preparation to initialize a feature store. First, we need to define the feature view. The feature view is a schema of the feature store. There are three main parts in the feature view. The entity defines the primary key of the feature view. For example, in the view of the customer, the entity is usually customer ID. And the features are what we want to use in machine learning models and maybe rule-based models or for analyze. The input defines the place to save the features. We use BigQuery as our storage here. After defining the feature view for our feature store, we can run Feast apply. Running this command will make Feast prepare the tables in BigQuery by the feature view we just defined. And Feast will register definitions, which will save the registry file to GCS. Then we can access the feature store using the provided SDK. Through the registry file, which was created in Feast apply. Here we can see the sample codes. Let's look at the features saved in BigQuery. Their schema is like this table. We have a column for entity ID, a column for timestamp, and a column and lots of columns for features defined in this feature view. By the way, the timestamp here is for helping us get historical features. The data stream will be looking like this. We use get historical features to access offline store and get the training set. Then we train and deploy the model. After deploy, we can access the online store and get the features by get online features for predicting. Another point here is the Feast. Another point here is in the Feast, the online store will be sync with the offline store, so we can make sure the data used in training and prediction are created in the same way. After feature store, I'd like to briefly introduce the training deploying pipeline in this part. The Vertex Pipelines is what we use for our training deploying pipeline for now. And it's a part of Vertex AI. And Vertex AI is the latest AI platform provided by Google. It allows us to build and deploy ML models on GCP easily. Vertex Pipelines is accessible through Kubeflow Pipelines SDK or TensorFlow Extended. And we use Kubeflow Pipelines SDK in our practice. Using Kubeflow pipelines directly will need us to create and maintain a Kubernetes cluster by ourselves, which means we need to deal with lots of permission issues and will be hard to start and maintain. Vertex Pipelines is easier to get started. It's responsible to provision all resources, store all the artifacts we want, and pass them through each of the steps. Which means we don't need to maintain the cluster and deal with all the permission issues. This is an important point for us since we want to spend more time on creating and improving models instead of the infrastructures. In general, we have three main parts as we discussed previously. First one is to get data from the feature store and save it as the Vertex AI dataset. Second is to train the model by the created dataset and save the trained model to GCS. Third, deploy the trained model to Vertex AI endpoint. We will discuss the three steps separately in the following slides. The process get data is done by running a Python script in a customer Docker container with the FIST SDK installed. The script accesses the FIST offline store and uses get historical features to fetch the features as data frame, then using toCSV to save the data frame in local, then upload to GCS as a Vertex AI dataset. The model training is done in a Docker container by Vertex AI custom container training job. The Docker image can make it possible to install all the necessary dependencies, deliver it easily, and use the Python script to customize the training process. Here is a sample code for the custom container training job. And next, we can deploy the model to the endpoint and start serving. After the model is deployed, we can access the endpoint and get the prediction result. Here is a simple code of how we get the prediction result using curl. Okay, and here is the overview of the whole model training deploying pipeline running on Vertex Pipelines. And these are our latest practice. We implemented the DataGate, the customer container training job, and we deploy the model after create the endpoint first. We are still working on add the evaluation into this pipeline. Finally, the last part. The feature store and the common training prediction pipeline bring lots of benefits to us. It allows us to focus more on model development and improvement. At the meantime, we can analyze the features or data more easily. So it helps a lot for improving model. And it increased our development efficiency by reducing a lot of duplication work for us. And we even got smoother onboarding and collaboration now, since we can onboarding all the projects to the new members with one single pipeline. Even though it brings lots of benefits, this architectures is still a tentative plan. We will keep improving it in the future. Here are some of our future plans. First, we want to create a common pipeline for the prediction process as well. We want to get more features. We are going to store prediction results or graph features in the feature store for analyze and modeling. One model's prediction result can be another model's input. And we want continuous monitoring and quality control are also important to us. We plan to use TFDV or Vertex monitoring to continuously monitor our models and features so we can improve our data reliability. And we also want to massively produce supervised models for growing requirements. Once we have new features or labeled data stored in the feature store, the training deploying pipelines will produce the supervised models automatically. Okay, that's all. Thank you for listening.